Remember that the Jacobian matrix has two parts, the rotational part and the linear part. We've just seen how to get the rotational part in the case where your joints are prismatic and in the case where your joints are revolute. We're now going to look at the linear part of the Jacobian. And once again, we'll find the linear part of the Jacobian differently depending upon whether our joint is revolute or prismatic. In the rotational part of the Jacobian that we last learned, we found that the rotational part of the Jacobian is easier when you have a prismatic joint. In that case, the rotational part of the Jacobian is all zeros. In the linear part of the Jacobian, it's also easier to find if the joint is prismatic, but it's not all zeros in this case. It might be a bit confusing, but in the linear part of the Jacobian for a prismatic joint, we find column I of the linear part of the Jacobian in the same way that we found the rotational part of the Jacobian for a revolute joint. In other words, we will take the rotational matrix from 0 to joint I and we'll multiply that times the vector 0, 0, 1. Actually, I have to have an I minus 1 as my subscript on this rotation matrix in order to make this work out. In other words, in order to find column 1 of the Jacobian matrix, I take the rotation matrix from frame 0 to frame 0 and multiply that by 0, 0, 1. In order to find column 2, I'll take the rotation from frame 0 to frame 1. This may seem a bit strange at first that we're using the same method that we used previously for revolute joints, now for prismatic joints. However, remember that the Jacobian matrix is being multiplied by the joint variable velocities. If I have a prismatic joint, the joint variable velocity will be multiplied by 0, 0, 1, since the rotation matrix is the identity matrix here. And so this will end up telling me that the velocity of the link, the linear velocity of the link, is the same as the joint velocity. Let's now look at how we find the linear part of the Jacobian in the case of a revolute joint. This will be a bit more complicated. In the case of a revolute joint, we find the ith column of the linear velocity Jacobian in this way. It starts out similar. We take Ri minus 1, multiply that by 0, 0, 1, but then we have to cross this value with the subtraction of the position of the end effector minus the position of joint I minus 1. In the next section, I'm going to do an example that includes both revolute and prismatic joints to show you how you come up with these matrices.